Hey, this video is on how we keep time. I talked about this a little bit on Zoom, so I'll just kind of briefly go over those things and talk about some new things. It's all stuff you should know. So have your practice tests out and are taking notes and whatever, because it's all really good stuff. You should know this stuff the rest of your life. It's awesome stuff. I love this stuff. Okay, so first, the year. Now, obviously, we know the year is how long it takes the Earth to go around the sun, but we also know it's more complicated than that. The ellipse year we talked about already. The ellipse year is called a sidereal year, and so that is, talking about years here. So that I wrote down as 365.25636 days, and that is called the sidereal relative to the stars. This is the true year. It's the one complete ellipse year. This is what it seems like we should be using, but we don't. We use what's called the tropical year, which is 365.24219, right? Slightly smaller. That many days. This is called a tropical year, and I keep meaning to look up why, but I don't know why it is. It's tropical. It's not like it's a warm year. Like I think a tropical is warm. I don't know. And this is the seasons year. We want to go by March 21st to March 21st. When is it spring? From equinox to equinox. From when the Earth is tilted this way to when the Earth is tilted this way. It's all about the Earth's tilt. Okay, so this is the Earth's tilt year. So this is a 23.5 degree tilt year. When that tilt lines up, and they're different because of the precession of the equinoxes, they call it, because that's what's happening here. The equinoxes change a little bit every year because the Earth's tilt changes. So this is due to the 26,000 year precession cycle. And it ends up being, like we said, about 20 minutes. The difference here is about 20-minute difference. So really, like we said, when it's New Year's, we go by this one. The actual ellipse year is here, so wait 20 minutes next New Year's, and then celebrate and go crazy, and everyone will look at, why are you doing that? Oh, because I celebrate ellipses, our full circle, not, seasons, whatever. And they'll look at you really funny, and really they'll think, wow, you're really cool. We appreciate that you introduced astronomy into this stuff, and you'll have lots more friends. So, yeah, so definitely use that to help. It works for me all the time. Okay, that's the year. Now the next biggest thing is the month. Obviously, the month comes from moon. They took out one of the O's, so it should be month, but they call it a month because a month is about 29.5 days, right? February is slightly shorter, but all the other ones are longer. We don't have 12 full moons in a year because we know that a month or a moon should be about 29.5 days, a full moon cycle. But multiply 12 by 29.5 and you come a little bit short of the 365 days. So we don't have exactly 12 or 13. It's like 12.3. I don't know what it is. You could do the math. We don't have exactly 12 full moons in a year, so months aren't perfect. So we have some months with 31 days and some with 30, and February with 28, except for once in a while 29. We'll talk about that. Okay, so that's the month. It's not perfect, but it works. A month. And then we have a week. Okay, and no one knows the origin of the week. It's the craziest thing. No one knows why we have weeks of 7 days. Some people think it's about the moon cycle, right? A quarter cycle is about a week because 4 quarters is about 29.5, but not really, right? Because 4 times 7 is actually 28 days. So a quarter moon cycle is a little bit longer than a week, but it's kind of the same. Other people think, again, it's kind of crazy, we don't know, that because there are 7 astronomical bodies in the sky that move, 7 things that are important that move in our sky, that they came up with 7 days a week because that's what they're named after. Monday is Moon Day, right? So y'all need to write down. Monday is Moon Day. Tuesday, okay, it's not obvious. We use the Teutonic names for the planets, okay? But think about Spanish. Lunes, lunar, right from Monday. Martes is Mars, so Tuesday is Mars Day. Lunes, martes, miércoles is Mercury. Wednesday is Mercury Day, and Wens is the name for Mercury, and again, this Teutonic language, which who speaks that? Thursday is Jueves, is Jupiter. It's Jupiter Day. Friday is Viernes is Venus Day. And the other ones are easy. Saturday is obviously Saturn Day, and Sunday is obviously after the sun. So the two big things in the sky, right? Monday and Sunday, Moon Day and Sunday. And then the 5 planets that you can see with just your eyes that move, right? Planets are the wandering stars. That's what that means. Planet in Greek or something means wandering star. The stars that tend to move through the sky. There's only 5 you can see well with just your eyes. Mercury, Venus, and then Mars, Jupiter, and Saturn. Earth doesn't count, right? We're on Earth. So some people think that's why. There's 7 objects in the sky that change their positions and move. That's why we have 7 days of the week. I don't know. But, okay, but that's weeks. Now, a day, we obviously know about days. We talked about how it's 24 hours. This is what's called a mean solar day. A mean solar day. And an average solar day, because any actual day is a little bit longer, a little bit shorter because of our ellipse around the sun. When we're going really fast around the sun, the Earth has to turn a little bit more, and so the days are a little bit longer than 24 hours, by like 11 seconds or something is the longest they're off. Some days are shorter than 24 hours. If you look, in other words, if you see the moonrise, or sunrise, and you see exactly where it is, and the next day you start your stopwatch, you stop your stopwatch exactly where it is, it's not always going to be 24 hours. Some day a little bit less. When we're going slow around the sun, the Earth doesn't have to turn as long to get the sun back up, right? Because we know we're a smaller part of our ellipse around the sun. So on the average, it's 24 hours. That's what we use. So even that one's complicated. Days aren't always 24 hours. The sun doesn't always rise exactly 24 hours later. Around January 4th, it's like 24 hours, 11 seconds when we're going fastest in our ellipse. Okay, so days are confusing. Then we have hours. And they talked about the origin of hours. Back in the day, like the Babylonians and stuff, they decided that there should be 10 hours in a day because they liked the number 10. Made sense. 10 hours of daylight, 10 hours of darkness. So it started off with 10 hours of daylight, and they said, well, we got to have 10 hours of darkness too. That's got to be fair. And then they said, well, but there's kind of like some light after it gets dark and some darkness, some kind of light before it gets light in the morning too. So they added 2 to that. They added 2 to those. To be fair, they had to have 2 here to get 12. So like 10 hours of the sun out, 2 hours where, the sun's kind of out, it's still light after the sun goes down. And so we get 24. You kind of add those up, and so we get 24 hours in our day. And 24 is a nice number. It's a convenient number. It's actually better than 20 because you can divide it by 2. And it's 12. You can divide it by 3. Can't divide 20 by 3 evenly, right? 4 divided by 3 is 8. You can divide it by 4, you get 6. Can't divide it by 5. You can divide it by 6. We just did that to get 4. It's going to be divided real easily. 60 is also a really good number. 60 minutes in an hour. 60 seconds, because 60 can be divided by so many different numbers. It can be divided by 2, by 3, by 4, by 5, by 6, not by 7, not by 8, not by 9, but by 10. 60 is a very easily divisible number, which also really helps it. Okay, so that's the minutes thing. The minutes and seconds. 60 is just such a nice number that they decided to come up with. Use that like 60 seconds and stuff. Just like 24, it's just so easily divisible. It's a nice thing to cut up in pieces, have different things there. So anyway, that's how we get all those things. Oh, and so the weird thing was back in ancient Egypt and stuff, when they always had 10 hours in a day. Well, just like us, we have longer days in the summer. So their hours were longer and during different times of year, and they were okay with that. So if you went to school, and in the summer, if your class was an hour, you had a longer period of time. In the winter, it was shorter. Craziness. Now, of course, we standardize it and make it all the same, but that's the way it was. All right, now what about our calendar? So first, way back in the day, they figured out there's about 365 days in a year. And so they had a 365-day calendar. And, that was all okay. But it's not exactly 365. It's about 365.25, roughly, right? We even know it's not exactly 0.25, but it's pretty close. So what happened was that if they had 365 days in a year, that's not quite enough days. And so pretty soon, since they weren't taking count of that day, they were missing days, right? So we're going a little bit not quite far enough to get to the next season, not quite far enough. So spring started happening every 4 years. We were missing a day, right? So times 4, we're 1 day off, we're 1 day short. We should have had that 1 day. So spring would start happening on March 20th instead of March 21st, then March 19th, and then March 18th, and March 17th. And spring started happening earlier in the year, and people were like, wait, we like to know that spring's always around March 21st, whatever. And it was happening earlier and earlier, or the solstices, all the major astronomical things that people measured back then. When is the sun the highest in the sky? The summer solstice. When is it lowest in the sky? The winter solstice. Or the equinoxes, when are days and nights equal. It kept changing because of that. So Julius Caesar, back in the days of Julius Caesar, he had some smart people that worked for him, and they said, you know, we need to fix this, because really, they figured out it takes about 365.25 days to go around the sun. That's pretty close, we know, right? Or between seasons, right? They didn't know about going around the sun, but between seasons. So they said, we need to keep this 0.25 in there. Every 4 years, we need to add an extra day, because every year if we drop that, we're missing a day. So they did that. That's called the Julian calendar, named after Julius here. So the Julian calendar. That was the first one to have leap days. Leap days. So every 4 years, they also changed the months around. They just like on July is named after Julius. They kind of, the months were all messed up. Now, anyway, they kind of got what we had now on the Julian calendar and had leap days. Every 4 years, they added an extra day in February. So every 4 years, we got a February 29th. Okay, so every 4 years, so that means we took track of that one. So every 4 years, right, we have one extra day, and that takes care of the 365.25. And it works pretty good because it's pretty close to that. However, we know it's not 365.25. It's actually 365, right, I just wrote it down, I'll write it down again. It's actually 365.24219. And there's even more decimal places that I left off because that's pretty good to get to that far. So it's actually a little bit shorter than that. So if we have an extra day every 4 years, that's too many extra days because it's really only every 0.24. Now, it's a small difference, 20-minute difference, really. But it adds up. Every year you get 20 minutes, and pretty soon it definitely adds up. And so, and people started noticing this. We were skipping too many days because it's not quite that many. And so in the 1300s, it actually, spring was happening again because they're skipping, we shouldn't have been skipping so many days. Spring was happening in the wrong time again because it was getting off because it's not 0.25, it's 0.24219, and they actually noticed this. And so let's see, how does that work? It's just so confusing, like would you add days? Basically, they had skipped too many days. Okay, so because they shouldn't have skipped so many, and so they were behind in time, right? Like it should have been March 21st and it was only March 10th, something like that. So they decided to change it again. They realized this was off. Now, if you do the math, and they were pretty good back then. It wasn't perfect, but they were pretty good. They realized that this means that you're off by 3 days. You skip 3 days too many. So you skip 3 days too many every 400 years. Okay, so every 400 years, if you do this, you end up skipping 3 days too many. That's what that, every 400 years. That's what this difference between 0.25, 0.24, 219 makes up. It ends up being about 3 days every 400 years. Okay, so they decide, okay, we have to not have a leap day, not have a February 29th, 3 times every 400 years. And they did this in like 1382. Okay, 1382. So they decided, which makes sense, that in century years, they decided to do it in century years, like 1500, 1600, 1700, 1800, 1900, because those are, nice round numbers. So in century years, they would not have a leap day. Okay, so no leap days. Filling up this board stuff. So they decided no leap days on century years. So this was in 1382. So like in 1400, there would be no February 29th. And in 1500, there would be no February 29th. And in 1600, and in 1700, but that's too many. If you do it, if you always do it, that's 4 every 400 years, not 3. So then they said, okay, the century year is divisible by 400 evenly. We're going to skip it. This makes sense. Divisible by 400. We're going to skip it. So 1600 is divisible by 400. So there would be no one here, and then yes, there will be one there. And then no in 1700, no in 1800. What's that thing doing there? No in 1900. But this one's divisible. 2000 is divisible by 400. So yes, there is a February 29th. So no, no, yes. And yes means there is a February 29th. There is a February 29th. There was a February 29th in the year 2000. There won't be a February 29th in 2100 or 2200 or 2300, but there will be in 2400. That way they're skipping 3 every 400 years. 1700, 1800 skip? Yes, here. Okay, got it. That makes the math here, the difference there, work out pretty good. It's not perfect. So like every year they'll add like, you know, the time people in like Boulder, Colorado, where they keep track, they'll add like a microsecond or, you know, to adjust it to make it perfect. But it's pretty darn close. This was Pope Gregory was the head of the Catholic Church then. So Pope Gregory the 13th was, okay, they usually don't put 13th, they say like IV or X333, right? That should be like XIII, 13th, they use Roman numerals, but whatever. Anyway, he was the head of the Catholic Church back then. The Catholic Church was a dominant force in the world. They had a lot of smart people working for him. So they started the Gregorian calendar. So instead of the Julian, it's now called the Gregorian calendar. The Gregorian calendar, the only difference really is the leap year thing. We're going to skip leap years and the centuries we just talked about. It's the only difference. Okay, the whole leap year thing. Pope Gregory got it right. Got it a little bit better. Much better than Julius got it. Julius is close. So, here's interesting story. So, the leap year, every 4 years there's a leap year now. Okay, so 19, and they're always like the presidential election years. They're the Olympic years, though this year we didn't have the Olympics because of COVID. But they are those years. Every 4 years, like 1996, 2000, 1992. I was born in 1964, which was a leap year. My mom was born in 1936, which was a leap year. When my mom's mom, my grandmother, was pregnant with my mom, she'd go into the doctor and they're like, oh, they looked at the chart and says, oh, your baby's going to be due on leap year on February 29th. By the way, it makes no sense. Leap year, they add a day. When I think leap, I think it's like jump over, skip a day, right? Instead, leap year is you add a day. It should be called add year or something. I've always been confused about that. Why is it leap? We don't jump over the day. We add an extra day. What's up with that? Well, whatever. So, leap year, back to my story. My mom the doctor said, oh, she's due on leap year. So on February 29th. And she was late. My mom was born on March 2nd. So she was like 3 days late from leap year. She was almost born on February 29th, which means she'd only have a birthday every 4 years, right? Then, when I was going to be born, my mom went to the doctor, and I was 1964. I'm now 56. Yikes. And my mom and the doctor said, oh, look at the charts. Oh, looks like, you know, your baby's going to be due on leap year on February 29th, because 1964 got it February 29th. And I was early. I was born on February 25th, so I was 4 days early from that. And then, when I got married and when my wife got pregnant with our first child, my daughter. She went to the doctor, and the doc said, oh, looks like your baby's due on February 29th. Third time in a row, right in our family. On 1996, when my daughter was born, which is leap year. And she was born on February 29th, and it wasn't induced. It was all natural birth, just by luck or whatever. It happened to be right. So the third time we got it right. My daughter was a leap year baby. She was born February 29th, 1996, which means she didn't have her first real birthday, first February 20th, until the year 2000. And fortunately, due to Pope Gregory, 2000 has a leap year. Or else she wouldn't have had her first birthday until she was 8 years old, till 2004. But because there is a leap year in 2000. Now in 2100, if she lives to be 104 years old, in the year 2100, she won't have a February 29th. She won't have that birthday. It's kind of sad. She won't ever be 104. So, you know, really she lived the same amount of time, but just there's no day to, you know, to recognize it. Okay, you get the idea. All right, so that was the whole leap year thing. Now, we talked about time zones. The railroad company started time zones in the United States in like 1883. Sorry. The other thing about the leap year thing is to make this right, to get spring back to February, to get spring back to March 21st, when they started the Gregorian calendar, because they wanted to get spring back to where it was like, I think they did it in October, and they said something like October 11th, they were going to make it into October 21st, or I'll have to look at those numbers exactly, but they actually skipped a bunch of days to get it back, the calendar back where it's supposed to be. So if you had your birthday that year or different things happening, they lost like 10 days to get it back. And they said that's what it's going to be. So like, what if you had to pay rent that month or something? You had a shorter month, you still had to pay your month's rent of rent. And you can see it's pretty messed up, but they did it, and good. It's good that they did. Got rid of that awkwardness back then. They actually skipped a whole bunch of days that year to make up, to get it back on track, because they hadn't been skipping enough earlier. Right? 3 days every 400 years. So by the first 400 years was 3, you know, from year 0 basically, Julian calendar. So by the time 1382, yeah, they're off by like 11 days. It's kind of crazy. All right, that's that. Okay, now gets complicated. So with leap year days, with time zones, so that everybody in a certain block has the same time, right? We don't want to go to Spokane and have a different time. Then we got off. So they basically broke up by longitude. Now we know that there are 360 degrees in longitude around the Earth, and we know that Greenwich, England is 0, the prime meridian. So if you divide that by 24, 360 divided by 24, which by the way, 360 is another really nice number that's divisible by lots of different things, you'll find that that's equal to 15. So there are 15 degrees per hour. The Earth turns 15 degrees every hour. And if there are 24 hours a day, 24 times 15 ends up being 360, return a full circle. So time zones are 15 degrees wide. Okay? Time zones then are about 15 degrees wide. That way everyone is an hour and you go 15 degrees. Okay, now we have a different time zone. It's a different time there, different time zone, different time zone. Makes sense. For political reasons, though, they don't always do it exactly in the longitude lines. They do it by state boundaries, by country boundaries. You have a small country and it goes right in between. You don't want to do it in the middle. So, you know, it doesn't always follow that 15 degrees, but roughly it does, because then it makes sense. The sun rises about when it should. Like on the equinox, the sun rises at 6, that's a 6, okay? So that's one thing. We have time zones. They call that time zones. Time is standard time, okay? So if you're on PST, that would be called Pacific. That's what we're on, because we're on the Pacific. Pacific Standard Time. That means we're using time zones, and it's just whatever the time is in the middle of the time zone. So it's the time, it's the solar time, the perfect time. The sun is directly overhead at noon, perfectly at noon. So it's solar time, actual solar time in the middle of the time zone. If you're on either side of the time zone, it's going to be slightly off in the middle of the time zone. Now, during certain times of year, as you guys know, they decide to give us less darkness in the morning, or more darkness in the morning and more time in the evening to have sunlight, because it's kind of nice. And so they call that daylight time. So we switch over from Pacific Standard Time to Pacific Daylight Time. So part of the year, we're on PDT, which is Pacific Daylight Time. They just changed the standard to daylight, right? So the D stands for daylight, and that means we're on daylight savings. We save some daylight until the evening. We save it to the evening so it stays light later, because most of us do stuff after school after work, whatever, you want to have some time after work to go do stuff. Because in the morning, who cares? It's dark, you get up, you go to school. Who cares, whatever. But in the evening, it's nice to have daylight. So they call that PDT, Pacific Daylight Time, when we have daylight savings, and they switch it back in the winter. There's the state of Washington passed a law, and so did California and so did Oregon, saying that we want to keep daylight time all the time. Switching back and forth, people have more, people have heart attacks. It's more because it's stressful. You got to wake up extra early some mornings, right, when the switch is back, and like, oh, you're all tired. And actually, it really hurts productivity. It's not a good thing for business. And so they want to keep it this way all the time. And I think it's great. That's what I'm for. But unfortunately, Congress has to let that go. The states just can't decide that on their own. It kind of affects the whole country. So Congress has to approve it. And for whatever reasons, Congress hasn't gotten around to approving it. So even though all the states say, yes, we want to do that, Congress hasn't approved it. So unfortunately, we still go back and forth between Pacific Daylight and Pacific Standard Time. Now, of course, in the United States, there's Eastern Time, EST. That's on the East Coast. So it goes Eastern Time, and then it goes, what does it go? I think it's, I know that in the middle it's Mountain Time. So it goes Eastern Standard Time, and then like Midwest Standard Time, Mountain Time. There's 3 time zones. So Eastern, and then gosh, what is it now? The middle, and then Eastern is 3 hours ahead of us. If you add 3 hours to our time, you get what it is in the East Coast in New York. So if it's 10:49 here, it'd be 1:49 there, right? And then there's the, I can't think of what it is. The other one, which is +2, and then there's Mountain Time. I'm thinking, Central. Central Time is +2. Eastern Time, Central Time, which isn't really central, but whatever. And then Mountain Time, you add 1 to us, and then Pacific Time, we add 0 to our time because we're there. So in 1 hour later in like Colorado, 2 hours later in like Chicago, 3 hours later in the East. So I guess 4 main time zones in the United States. Yeah. So let's go. Yeah, good stuff here. Okay, let's go back to this. 15 degrees is an hour. Okay. So what is a degree? If you go 1 degree in longitude, if you travel directly east or directly west, you go 1 degree in longitude, then you go 1/15th of a time zone. Okay, so an hour is 60 minutes, so it's 15 degrees for every 60 minutes. So if you divide everything by 15, that's 1 degree is the same as 4 minutes. So if you go 1 degree in longitude, like I go towards Idaho and I go 1 degree in longitude, the sun will rise there 4 minutes earlier. It's kind of cool. If you like early mornings, you want to live on the east side of the time zone. It's the same time in Spokane and in Seattle. Same time. 8 o'clock is 8 o'clock. However, the sun rises earlier in Spokane. And if you're on the, and they're not, but Spokane's pretty close to like the eastern edge of the time zone. So let's say one town was on the eastern edge, one time is the western edge. It's an hour difference. That's what a time zone is about an hour. So if that was the case in Seattle, and they're not perfectly like that, but it could be, then like if the sun rises at 6 o'clock in Spokane, it rises at 7 o'clock in Seattle. So if you like nice bright mornings, you want to live in Spokane. If you like bright evenings, you want to live in Seattle. Stays light an hour later. Now it's not quite that much difference, but I think it's at least like 45 minutes. So Seattle people have lighter evenings, but darker mornings. Spokane people have lighter mornings, darker evenings. It's kind of weird. That's just the whole time zone thing. So every degree you go in longitude is 4 minutes. So let's pretend that Wenatchee was 2 degrees away. Then the sun rises in Wenatchee about 8 minutes before Leavenworth. It's not that far. But that's the way that works. So you can figure out how much earlier the sun rises by knowing how many degrees longitude it is away. It's pretty cool. Okay, what else do we need to know here? I'm trying to work through the practice test, make sure I go over a lot of the answers. Okay. Okay, yeah, so October 4th, I have to look that up. October 4th became, I think it was October 21st. So I got this wrong over here. For Pope Gregory, October 4th, he made October 4th into October 21st to get spring back to to March 21st. That's how that works. Okay, now at noon, by definition, noon is when the sun is highest in the sky. Okay, but it's not. If you go outside today at 12 o'clock, the sun will not be highest in the sky. It's always highest in the sky when it's directly south. So if you look, here you are, if you look directly south, and if here's the sun, that's when it's highest. Okay, it goes up, comes down, so it sets more or less in the west, rises in the east. It's always highest when it's directly south. But it won't be directly south, normally at 12 noon. That's if you're on local solar time. If you're in the middle of the time zone, if you're in our exact middle of the time zone, and you are, and it's standard time, not daylight time, then that might be the case, okay? So in Leavenworth, we're not in the middle of the time zone. We're actually kind of close-ish, but we're not. So that's one reason why the sun isn't directly up. The other one is we're on specific daylight time. We're on daylight savings. It's an hour off. So really now it'd be 1 o'clock. Okay, so it should be 1 o'clock. So that's another reason why it's off. It's daylight savings time. The other one is we're not in the middle of the time zone. We don't go by local solar time. We go by standard time. And the third one is days aren't always 24 hours, right? We know that sometimes the 24 hours 11 seconds, sometimes they're 11 seconds short. So even if it was noon exactly one day, if we waited 24 hours, it could be 11 seconds off because of our elliptical orbit. So those three things make it so that the sun is not always highest directly in the sky. The fact that days aren't always 24 hours, even anywhere in the world, by a certain thing, it's only going to be exactly noon a couple of days of the year, because of the fact that days aren't always 24 hours, which is what we go by. So it's perfect one day, the next day it's going to be off by up to like 11 seconds. So that's one of the reasons why, again, the sun isn't highest in the sky at noon. And, yep. Okay, cool. I think I've gone over most of this. We can go over some more of the other stuff later. So time is complicated. It's kind of fun, though, understanding all these things. Oh, yeah, that is one other thing. You had something. The time in Greenwich, in England, and it doesn't go just through England, it goes all the way through the Earth. At Greenwich, which is 0 degrees longitude, which is the prime meridian, they call it the main longitude line, the prime longitude line, they call those meridians. That's got a special time. Okay, the time there is like time 0. Okay, time 0 is the time there. So they have a special word for that. Actually, there's lots of words for that. They call it universal time, so UT. So the universal time is the time in Greenwich. Then they decided, well, I don't know why they decided this, but then they said, you know what, let's call it universal time coordinated. So UTC. So now you typically see it, but why is it coordinated? Why is it just, I don't know, but anyway, UT or UTC or Greenwich Mean Time. You often see this one, Greenwich Mean Time, which is GMT, okay, is also the same thing. So this is the same thing as GMT, same UT is the same as UTC, is the same as GMT, and it's also called Zulu time. Because something about that line is the Z line, and Zulu is what they use for the letter Z, just so, because Z sounds like C, so you say Zulu, so you know you're talking about Z. So those are all the words for the time in Greenwich, England, the time that everybody goes off of. We always compare our time to Greenwich, England. We are 8 hours before the time in Greenwich, England, if we're not on daylight savings time. So we are at -8, we'd say. You take the time, this is our Pacific Standard Time. Not Pacific Daylight Time, Pacific Standard Time. Daylight Time are -9. So if you take the time in Greenwich, England, you subtract 8 from it, that's the time here. So if it's 9 o'clock in the morning in Greenwich, it's 1 o'clock in the morning here. Scientists use this. When I was doing research at the University of Washington, we're plotting things that happened in the sky, like lightning strikes and the aurora borealis and stuff, plotting it versus time. We always use universal time because everyone knows, oh, that's the time in Greenwich. Otherwise, it's like they're using standard time, using Pacific time, Eastern time. You just always plot it by universal time, and everyone knows, can compare. It's much easier than having to convert time zones. Everybody uses universal time. Okay, so those are all different ways to measure time and compared to Greenwich, and then you say how your time, local time, compares to it. -8, +2, wherever you are on Earth. Phew! Okay, long video. Hope you took some pauses, stopped it every once in a while. Good stuff. I think this stuff is awesome. And hope it all made sense. Thanks for listening. Goodbye.